Hello again. Hello again. This is Math 2115 coming to you from the College of DuPage. The title of this lecture is Definitions and Calculations Using Big O, Omega, and Theta Conventions. And as always, please be an active learner as you watch this video. In the last section, we talked about what an algorithm was, and we introduced algorithms that solve certain problems, including searching for an element in a list and sorting a list, a couple of ways to sort the list. Looking forward, we're going to study the number of operations used by certain algorithms, and we'll estimate the number of comparisons used by linear and binary search algorithms to find an element in a sequence of n elements. And we'll also estimate comparisons by using the bubble sort and by the insertion sort to sort a list of n elements. Now, sometimes we're interested in the time required to solve the problem, and that certainly depends on more than the number of operations it uses, but it does depend on the number of operations. It also depends on the hardware and software that you're running the problem. However, when you change the hardware and software, because technology always change, you can closely approximate the time because the number of operations remain the same. And so to do this, we use notation called the big O notation, omega, and theta notations. So, and that will allow us to estimate this, and we're basically separating the complexity of the algorithm versus the speed of the technology. So one of the advantages of using the big O notation, which we're introducing here, is that we can estimate the growth of a function without worrying about constant multipliers or smaller order terms. This means using big O notation, we do not have to worry about hardware and software changes. Moreover, using the BO notation, we can assume that different operations used in an algorithm take the same time, and that simplifies the analysis considerably. So here's the definition of big O. So let f and g be functions from the set of integers, or the set of real numbers, to the set of real numbers. We say that f of x is big O of g of x if there are constants c and k such that the absolute value of f of x is less than or equal to a constant c times g of x whenever x is bigger than k. And we read this as f of x is big O of g of x whenever this definition is true. Now, intuitively, this means that whenever we say f is big O of g, that f grows slower than some fixed multiple of g as x grows without bounds, and that means eventually this domination happens, and that is in the long run. Now, the constants c and k in the definition of the BO notation are called witness to the relationship that f of x is big O of g of x. So to establish that f of x is big O of g of x, you need to find and demonstrate one pair of witnesses. That is, to show that this is true, you need to find one pair of constants c and k, the witnesses, such that this is true whenever x is bigger than or equal to k. Now note that when there is one pair of witnesses, you could have infinitely many pairs of witnesses, and so you could pick one, but you only need one. And so to see this, you notice that if I pick c prime bigger than c and k prime bigger than k, then if c and k are witnesses, then c prime and k prime are also going to be witnesses. Okay, so let's work with this a little bit, and here is a very useful approach. And what we're going to do is first select a value of k for which the size of the absolute value of f of x, or f of x, this is a positive function, can be readily estimated when x is bigger than k. And then see if we can use this estimate, having picked k, to find a value of c for which the absolute value of f of x is less than or equal to cg of x for x greater than k. So let's look at a problem. So here's our first example, and you're being asked to show that f of x equal x squared plus 2x plus 1 is big O of x squared. Well, we're going to take x bigger than 1. And the reason we take x bigger than 1, because if x is bigger than 1, then x squared is bigger than x. Now, if x is less than 1, like 1/2, if you square 1/2, you get 1/4, so it doesn't go the right way. But if we take x bigger than 1, this is true. So x is less than x squared. And also, if I then square x and x is bigger than 1, x squared is bigger than 1. So here's the inequalities that we can get. So 0 is less than or equal to x squared plus 2x plus 1. But you see, x is less than x squared, so x squared just matches up with x squared there. 2x, we know that x squared is bigger than x, so 2x is going to be less than 2x squared. And here's 1, and x squared is also bigger than 1. So you see, I've done this estimate. I've replaced everything by something that's bigger than or equal to, and I have 4x squared. Now you see, what we've done is we have shown when x is bigger than 1, that the function that we had, and the absolute value of this function, this is always positive, is going to be less or equal to 4x squared. So what we have is the witness is x is bigger than 1 and c is 4. Now we could have done different numbers and done different kinds of things, and you might want to look at this example, but we have demonstrated that f of x, x squared plus 2x plus 1 is big O of x squared. And if we looked at a picture, what that means is that here's the graph of x squared plus 2x plus 1. And if I look at the graph of 4x squared, that gets bigger and stays bigger after I am at 1. And so you see that that demonstrates what we have. Now, you should observe that in the relationship f of x is big O of x squared could be replaced by any function with larger values than x squared. So we could say, for example, that f of x is equal to big O of x cubed, or f of x is big O of x squared plus x plus 7, and so on. It is also true that x squared is big O of x squared plus 2x plus 1, because x squared is less than adding positive numbers whenever x is bigger than 1. So again, c equal 1 and k are witnesses to the relationship that we had. You should also note that we had two functions, and so f was big O of g of x, and in this case, g of x is also big O of f of x. And we can multiply the inequality, this one, x squared is less than or equal to x squared plus 2x plus 1, which holds for all real numbers x. So we can say, whenever we can say, that two functions f and g both satisfy being big O relationships of each other, they're of the same order. And we'll talk about that later. But in this case, it was true. We're going to see that it is not always the case. Okay, here's some more notation. The fact that f of x is big O of g of x is sometimes written f of x is equal to big O of g of x. However, the equal sign does not really represent a genuine equality. It really just says that an inequality holds regarding the values of f of x and g of x for sufficiently large numbers in the domain of the functions. It is acceptable to say f of x is an element of big O of g of x because this is a set of functions that are big O of g of x. When f of x is big O of g of x, and h is and f of x is big O of and h is big O of g of x. Let me do this again. So when f is big O of g of x, and g of x is big O of h of x, it follows that f of x is big O of h of x. So you see, the big O relationship is a transitive relationship. So if we start with this being big O of g of x, and if h is bigger than g, then it's also big f is also this. So big O is a transitive relationship. And here you see a geometric interpretation of that. Now, in subsequent discussions, we will almost always deal with functions that take on only positive values. And so all references to absolute values could be dropped if you're working with BO estimates for such functions where they're always positive. Okay, so let's do another example, and here's what I'm asking you to do, and I am going to give you this as a little assignment. So show that 7x squared is big O of x cubed. So what you want to do is work on this, and you know what to do. Let's see how you did. Okay, well, again, we have to find k. So we note that when x is bigger than 7, 7x squared is less than x cubed, because to go from here to here, we multiply both sides of x bigger than 7 by x squared, and we get this. We're multiplying by a positive number, so that doesn't change the sense of inequality. So we can take c to be 1 and k to be 7 as witnesses and establish that 7x squared is big O of x cubed. Alternately, when x is bigger than 1, we have 7x squared is less than 7x cubed. So c is 7 and k and 1 are also relationship, are other example witnesses to this relationship. So 7x squared is big O of x cubed. But things are not always true. We're going to show that n squared is not big O of n. To show that n squared is not big O of n, we must show that no pair of witnesses, c and k, exist such that n squared is less than or equal to cn whenever n is bigger than k. We're going to use a proof by contradiction to show this. So suppose that there are constants c and k so we're assuming that there are constants for this, so that n squared is less than or equal to cn whenever n is bigger than k. Now notice when n is bigger than 0, you can divide both sides of this expression by n and not change the sense of the inequality. So when you do that, if we divide both sides by n, you get n is less than or equal to c. You see that's no matter what c and k are, n is less than or equal to c cannot hold for all n with n bigger than k, because you could take n to be a bigger and bigger number. And so you see it's not bounded above by the c. In particular, once we set a value of k, we can see that n is larger than the maximum of k and c. So therefore, it's not true that n is less than or equal to c, even though n is bigger than k. This is a contradiction, and our assumption was this was big O of n, so the contradiction means n squared is not big O of n. Now, here is another example. And what we're talking about here is we've just shown that 7x squared, this was the previous example, was big O of x cubed. And the question is it also true that x cubed is big O of 7x squared? Well, again, we're going to look at a proof by contradiction. So determine whether this is this. We need to determine whether witnesses c and k exist such that x cubed is less than or equal to c times 7x squared whenever x is bigger than k. And we're going to show that no such witness exists because we're going to use a proof by contradiction. So if c and k are witnesses, then what happens is that means that x cubed would be less than or equal to c times 7x squared for all x bigger than k. Now this is equivalent to the inequality, and what we're going to divide is divide both sides by x squared, which is a positive number. So this, if you divide both sides by x squared, this is x is less than or equal to 7c, which follows by dividing both by the positive number x squared. However, no matter what c is, it is not the case that x is less than or equal to 7c for all values of k, no matter what k is, because you could pick k to be 10c, where c is a positive number. since x can be made arbitrarily large. This means x can be arbitrarily large. It follows that no witnesses, C and K, exist for the proposed big O relationship. Therefore, x cubed is not big O of 7x squared. And notice that 7x squared was big O of x cubed, but x cubed was not big O of 7x squared. That means that big O is not a symmetric relationship. Now we can talk about big O estimates of some important functions. And so here's an important theorem. Suppose you have a polynomial, and you might remember from your algebra that the end behavior was determined by the leading term, and that's going to be true here. So if f of x is a polynomial, an nth degree polynomial, and those are real numbers, then f of x is big O of x to the n. And you see what we can do is we can say that the absolute value of f of x is equal to the absolute value of the polynomial. And then this is less than or equal to the absolute value of each individual term. And since we're taking x to be bigger than 1, when I raise x to a power, it is bigger than that. So what I can do is I can factor out the x to the n out of here, and I get x to the n times all of these coefficients. Now notice here, I'm dividing by numbers that are greater than 1. So all of these terms are dominated by a sub n minus 1 through a sub 0. So you see this is less than or equal to that. This shows that the absolute value of f of x is less than or equal to cx to the n, where c is the absolute value of a sub n and the sum of the coefficients whenever x is greater than 1. Hence witnesses tell us that c can be the summation of those coefficients and k can be 1. That shows that f of x is big O of n. Now here's a problem I'd like for you to address. So try to use big O notation to estimate what is big O of the sum of the first n positive integers. You know what to do. And we'll see what you did when we come to the conclusion of this lecture. But for now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.